Okay, problem 3 looks like kind of a doozy. It's actually not as bad as it might appear. Though this is, in a way, it's the hardest of the 3. So we got a block attached to a spring. It's got some spring constant, which we know. And so let me draw my little block here. And it's got a mass, which we don't know. It's got a spring constant, which we do know. And we'll just say it slides. Ugh. Let's see. It slides along a horizontal-ish surface. Something like that. And we're going to say right now, let's see. So right now, we're going to say this is the positive x direction. And we're going to say, so these conditions here are at some point in time, at some time t, the position is x equals this, positive 1.00 meters, v is negative 13.6 meters per second, and a is negative 123 meters per second squared. Okay, so that means it's displaced in the positive x direction, but it is moving in the negative x direction, and it is accelerating in the negative x direction as well. Okay, so here's how it works. It's not nearly as bad as you think. First of all, you measure the position of the block from the system's equilibrium position, right? So it is 0.100 meters to the right of the equilibrium position. Now, recall how the force, the spring force, works on this block. It's going to be, the force from the spring is going to be negative k times x, right? So we know the spring constant, don't we? And we know what this x is right now. So we know there what the mass is. Or sorry, we know what the force is. Recall also, force equals ma. So now you can put these two together, and you can say ma equals negative kx. Okay? And then, let's see, we want to find, well, one of the things we want to find is the mass of the block. So we can easily solve this here. M equals negative kx over a. And these are all known, right? A is known. We were given A. We were given K right up here, little k, and we're given X. So this already here gives us the answer to part B. And we didn't even have to know, jack. We didn't have to know anything about single harmonic oscillators, or simple harmonic oscillators, sorry, to solve for the mass. Already we've got it. I mean, that's pretty good, right? That's fantastic. Okay. So then let's look for what would come next. The frequency of the oscillation or the amplitude of the motion. So let's look at the frequency first. And recall that frequency, so let's go for blue for B. Recall that frequency is related to angular velocity, omega, like this. Omega is 2 pi f. And if you pull out your handy-dandy, one of your handy-dandy little factoids about simple harmonic motion, it would be that omega is equal to the square root of the spring constant, little k, sorry, let me make it a little bigger, of the square root of the spring constant, lowercase k, over the mass, m, right? And you might remember this, or you might have to go through the whole process by taking derivatives. So you'd say, look, x equals a cosine omega, cosine omega t. So then v, which is dx dt, is cosine, derivative of cosine is negative sine, so negative omega a sine omega t. And then a is dv dt, which is then the derivative of this, which is negative omega squared a cosine omega t. And then, because, let me find a good color, pastel blue, baby blue, okay? Because this, a cosine omega t, is also this, you get a equals negative omega squared x, okay? And so omega squared, well, we also had a equals negative k over m times x. If you take this here and also say a equals negative k over m times x, And so therefore by inspection you can get to this. You can get to this by inspecting, let's see, where are the colors I was using? There we go. That's a little bit light. But inspecting this and this, come on, there we go, leads you to this here. That omega equals k over m, okay? Now, was I using sort of cobalt blue there? No, I wasn't. Okay. I can't believe I care. Alright, so, but anyway, the point is then you can get from these two to f equals omega over 2 pi, or f equals square root, let me do it like this, f equals square root k over m divided by 2 pi. Not terribly good penmanship, but if you wanted good penmanship you wouldn't have been looking at my videos, would you? Okay, so that gives us part A, it gives us the frequency of the motion. Okay, so now we got that. We've already gotten the mass, right? So all that's left is the amplitude, and look, we've barely done anything, right? So now, you know, amplitude. This promises to be kind of annoying. So let's see. Yeah, there's probably no way to do this other than with an energy balance. So, or probably the easiest way anyway to do it is with energy balance. So for part C, actually let me use purple. So C is in purple. Okay, so you're going to have to go E mech is, yes, you guessed it, 1/2 k x squared plus 1/2 mv squared. This is our kinetic energy here, 1/2 mv squared. This is our potential energy here, 1/2 kx squared. I'm just not writing the whole thing out this time, but it should be familiar by now. So then you really, what you're going to have to do is plug in these guys. So we know, at this point we know k, we know m, we know x, and we know v at this one point in time, right? So you take these two as well as your k, and so the k we had before, this is k, and we got m here. So you plug all those in, and then so you find what E mech is, and then you say that at x equals a, your speed, when x equals a, that is when this guy has reached its maximum x, position, then when x equals a, v equals 0. So that means E mech equals 1/2 k a squared plus 1/2 mv squared, which is going to be 0 there. So then you just have to solve, I mean, I guess if you want to put all this together you can. I suppose, should I? Well, why not? I'm bored. Okay, so we're going to take this, and x and v are going to be your, the ones they gave you in the problem. We're going to 1/2 k x squared plus 1/2 m v squared equals 1/2 k a squared plus 0. So this is just energy balance at 2 points in time. That's this and this, setting them equal. Okay, and then let's see. I guess we can cancel all the 1/2s and divide through by k. We want to find amplitude, right? So then you can get x squared plus m over k v squared equals a squared. And m over k, I think we can recall, is 1 over omega squared. So however you want to do this, you can go, let's go a squared equals x squared plus m over k times v squared. I'm really doing this for my own amusement. What you should do is, if you're trying to solve this on a test, okay, is just use this to find E mech, like I said, and then plug in, you already know k here, plug in the E mech you got and just solve for a and you're done, okay? What I'm doing right now is just sort of taking this to just an extreme. But the other thing you really could do if you wanted to is you could take this guy and then substitute in this expression we have for the mass, and it's negative kx over a. So negative k, that's going to cancel. So then you would get a squared equals x squared minus, and then negative k minus x over a times v squared. And wow, I mean, is that taking it just way too far or what? So yeah, there we go. If you really wanted to solve for it entirely symbolically, you could do it. This x and a and v would be the initial, or not the initial, but the conditions they give you at that time t. Okay, anyway, that's way too much. I hope that helps people. Good luck on the test tomorrow and Friday, and I hope you can still enjoy J-Day afterwards.